Hey, so this is Joseph, and this is the third video in the seventh chapter of Stewart's calculus, and we're going to be talking about the partial method, or the partial fraction method for solving integrals. So the basis of this method is we're going to be using the following identity to substitute in some function that we're trying to integrate, so then we can break it up and integrate it and have a bunch of little integrals that are easier to solve. So the main identity working here is going to be this one. So if you've got a fraction where on the numerator there's any kind of polynomial, and on the bottom there are certain functions of x multiplied by one another, that will equal, so if there are three functions of x multiplied by one another, we'll get three fractions resulting in a over the f of x plus a b over the g of x and a c over the h of x, and the a, b, c correspond to some breaking up of this polynomial. And if there are only two functions multiplied in the denominator, we'd only get three resulting partial fractions. So this is the rule that we're going to be dealing with, and that's going to be kind of the crux of the partial fractions method of solving integrals. So your book kind of tries to make this rule generalized, and I think that the generalized way that they try to describe is a little bit more confusing than just going through the method when we solve a problem. So that's what we're going to do. And there's really only one kind of problem with this. You could have, multiple functions in the bottom and then multiple resulting fractions, but the method that you're going to use is going to be the same regardless. So we're just going to do one problem. I'm going to go slowly through the method so that it kind of becomes clear. Alright, so we're going to start off doing number 10 on page 516 in your book, and we know that we're going to have to use the partial fractions method to solve this integral because we can't use a u substitution, and we've got a polynomial in the numerator, and then multiple functions of, well, in this case, y, multiplied by one another in the denominator, 2 to be exact, so we know we're going to get two resulting partial fractions. And sometimes, when you will need to use the partial fractions method even if there's a polynomial in the denominator, but if it's a factorable polynomial, factor it and then use the partial fractions method, but this one's already factored out for us. So what we're going to need to do first, before we start dealing with the integral itself, we need to sort of simplify this expression using the rule that I showed you on the previous screen. So we will have y over y plus 4 times 2y minus 1, and that is going to equal some a, which is presumably going to be some function of y, over y plus 4, plus some b over 2y minus 1. So, in order to so now what we need to do is we need to figure out what this a is and what this b is, so then we'll be able to integrate these two fractions, and as you can see, those will be pretty easy to integrate. So we will multiply this denominator over onto this side, and we'll get y equals the y plus 4's will cancel out there, so we'll get 2y minus 1a plus, and then the 2y minus 1a will cancel out on this fraction, and we'll get y plus 4b. So now what we need to do is we need to plug in for values of y kind of skillfully and be sort of clever about it. And what I mean by be clever is basically choose values of y that'll make one of these terms disappear. So for example, when we plug in for y equals a half, this coefficient becomes a 0 and the a disappears, and we only deal with the b. So we'll plug in for y equals a half, and so we'll get 1 half is equal to 0 because the 2's cancel, and that's a 1 minus 1, and so that's a 0, plus, and then that will be a half plus 4b, and so we'll get a half is equal to 5 halves b, and we get b is equal to 2 fifths. Or sorry. We'll get b is equal to 1 fifth. So there we go. We've got half of this simplification done. Now we're going to need to plug in a value that'll make b disappear so we can deal with a, and let's do that on the next screen. So we'll get 1 half is equal to 0 plus 1 half plus 4b, which will equal a half, and then that 4 halves, that will turn into 9 halves b. Then you multiply this over, and we're going to get b is equal to a ninth. And so now we're going to have to do the same thing for a. We're going to have to make the b term disappear and just deal with the a. So we'll do that on the next screen. So we need to ask ourselves, what will make this term equal 0? Well, negative 4 plus 4, that's 0, so we're going to plug in for y equals a negative fourth. So we got negative 4, and that will be equal to negative 8 minus 1, a, and then plus 0. So we're going to get negative 4 equals negative 9, a. So a is going to be 4 ninths. So now we've got a, we've got b. Now all we need to do is plug this in and figure out what our new expression that we're going to integrate is. So if we've got a is equal to 4 ninths and b is equal to ninth, and we've got y over y plus 4 times 2y minus 1 is equal to a over y plus 4 plus b over 2y minus 1. That is actually equal to, when we plug in the a and the b, it's going to be 4 ninths over y plus 4 plus a ninth over 2y minus 1. So, since our initial task was to integrate this function here with respect to y, all we'll need to do to solve that is then integrate this function with respect to y. So let's come down here. We can break this up because we've got a plus in the middle, so we can make that 4 ninths y plus 4 dy plus the integral of 1 ninth 2y minus 1 with respect to y. And now we can do u substitutions here, and then we'll get a natural log function. But we know that when we take the derivative, if we set u to y plus 4, we take the derivative of that, the derivative is just going to be dy. So we know that we're going to get the u back in the argument of the natural log, so we can just write that directly, but with the coefficient, because we need to keep that coefficient. So 4 ninths, the natural log of the absolute value of y plus 4, and remember that absolute value sign. So that's that integral, plus, now when we set u equal to 2y minus 1, we're going to get du is equal to 2 dy, and we're going to need to take care of that 2 by dividing it. So we would get a half times a ninth, the coefficient there, times the natural log of the absolute value of 2y minus 1 plus c, and then that'll turn into an 18th. Absolute value plus c, and that is that integral. If you really wanted, you could use your natural log rules, and because these are added, you could multiply the arguments, but we don't really need to do that because then you need to take care of these coefficients. But that is how you use the partial fractions method, and if you were to divide it up into 3 fractions, you do the exact same thing. You try to isolate each term in that equation that we made earlier, or you'd have to end up doing a system of equations with 2 variables. But that is Algebra 2, and you should be good with that. So stay tuned. We're going to be talking about improper integrals next, and convergent and divergent integrals. So stay tuned. And also, this is kind of the last of the advanced integration techniques that you're going to need to know. So now you should be able to, with the techniques that you've learned thus far, you should be able to solve just about any integral that is thrown at you in either Calc AB or BC. So be excited about that.